Well, good afternoon and welcome everybody. It's great to see you all here. I'm David Gerdes. I'm the chair of the physics department, and it's my pleasure to welcome all of you, those of you here in the room as well as our audience watching the live stream on YouTube, to the 2024-25 Taya Wu lecture presented by Professor Hirosi Ooguri from Caltech and the University of Tokyo. Now, before I go on, I have an important announcement to make. If you left your phone over in the reception, someone reading a C++ book, so you're probably a high-energy physicist, this is your phone. Okay. Okay, so the Taya Wu lecture series was endowed by Taya Wu's friends and admirers to honor his remarkable life and legacy as a scientist, teacher, and national leader. The Taya Wu lectures began in 1992 with a lecture by the Nobel laureate C.N. Yang, who was a student of Dr. Wu. Indeed, Taya Wu's most enduring legacy may be the generations of students that he influenced, both directly as their mentor and teacher, and indirectly through a series of highly influential textbooks that he wrote. Dr. Wu was born in China in 1907 and earned his PhD from the University of Michigan in 1933. His early work was on the chemical properties of a hypothetical class of elements heavier than uranium, the transuranic elements, and he predicted their chemical properties before they were subsequently discovered in the 30s and in the 40s and later. Over the course of the next 6 decades, Dr. Wu carried out his research in Canada, the US, and Taiwan. In Canada, he led the Theoretical Physics Division of the National Research Council, Canada's equivalent of the NSF, and returned to Taiwan in the early 1960s, where he served as president of the Academica Sinica from 1983 to 1994. He continued lecturing and teaching into his 90s, and his legacy as a teacher endures today through educational events like this. In addition to honoring the legacy of Taya Wu, this lecture also celebrates the accomplishments and career of our speaker. In the 32 years since its inception, this lecture series has provided a stage for luminaries from all fields of physics to present their work and inspire our audience of faculty, students, and members of the public. To introduce today's speaker, Professor Ooguri, please welcome my colleague, U of M physics faculty member Finn Larson, to the stage.
Thank you. So today's speaker, Hirosi Ooguri from Caltech University, Caltech Institute of Technology, is well known, at least for me, already very early on when I was a grad student, as being a prodigy. He received, if I understand it correctly, his PhD in just 2 years and immediately went on to become tenured professor at the University of Tokyo, the top university in Japan. After that, he went to the US and were at multiple distinguished institutions, also as faculty, and made it after a few jumps, different places, in Princeton, in Berkeley, and then to Caltech, where he is now a professor. He was ever since 2000. He was the first Kavli chair at Caltech, and as many people know, Kavli is a major donor also in our field. He was the founding director of the Walter Berg Institute, which is a major theoretical physics institute at Berkeley, and was also part of the founding of the IPMU, which is the major institute for the physics of mathematics of the universe at the University of Tokyo, which is the key research institute in Japan for that. So apart from those organizational things, he obviously has been incredibly influential in string theory, in quantum gravity since the very start, since he really did get in the young age and come in on the bottom floor. He's contributed remarkably to nearly all aspects of string theory, and that's part of the versatility that makes him famous. In addition to that, he's gotten, of course, a number of awards in Japan. In the US, he's a member of AAAS. But he's also known for being a great presenter. He has written public books, sold over 250,000 copies in Japan, and been on bestseller lists. So that makes our expectation for a great presentation even that much higher. So we welcome Professor Ooguri, and he will give this year's Taya Wu lecture.
Thank you, Finn. Thank you very much for your overly generous introduction and also putting me in some kind of tension in sort of delivering what he advertised, and I'll try my best to do that. First, I need to move my pointer to the appropriate location. Can you see my pointer? Okay, so it's my great honor to present this year's lecture. Wu Tayo was a very important person in science, but also important mentor, and so it's a great honor to give this lecture. So today, I'd like to tell you about quantum gravity. Now, this is a work in progress, and I'll tell you what's known and what's not known and what I would like to know about. So I'd be happy to share this with you. So first, definition. So when I talk about quantum gravity, so there are two pillars of modern science, general relativity and quantum mechanics. And so this is sort of a unified framework to describe both theories in the same mathematically consistent framework. And as I said, this is a work in progress. The quest toward quantum gravity has had a really long history. General relativity was formulated in 1915, already 109 years ago. And then this year celebrates the beginning of modern quantum mechanics. And it was formulated between 1994 when de Broglie formulated wave mechanics to the matrix quantum mechanics of Heisenberg and Schrödinger's wave equation. Now, so there was big important development was in 28 to 29, where people like Dirac, Heisenberg, and Pauli formulated unification of special relativity and quantum mechanics. So special relativity was formulated much earlier, 1905. And so the requirement to unify special relativity and quantum mechanics in a single framework led to the idea of quantum field theory, and in particular, quantum electrodynamics in this case, which is quantized version of electrodynamics. And it turns out that this theory has some difficulty when people try to calculate various important quantum mechanical effects. It leads to some nonsense result with infinity all around. And the way to deal with it, figuring out that took 20 years and eventually led to the discovery of the scheme of renormalization. And people, of course, started to think about unification of general relativity and quantum mechanics. And as I will show you in the next slide, it leads to the discovery of Faraday-Popov ghost. And then only after 50 years, half century after the formulation of quantum mechanics, we found at least one framework in which to describe unify general relativity and quantum mechanics in the single framework, which is a string theory. And we have been studying this theory and its consequences for the last half century. As I said, it's still work in progress, but I'd like to tell you about what's known and not known about this approach. But the study of quantum gravity has already had a very important impact in high-energy physics. For example, in 1962, around this time, Richard Feynman was very interested in quantum gravity. And so he tried to apply his Feynman diagram method to do calculation in quantum gravity. And in quantum field theory, one of the important observable is S matrix, which tells you when particles come in and interact with each other and come out, what's the probability of this process. And S matrix allows you to calculate quantum mechanical probability of the process. Of course, the probability has to sum up to 1, and the probability has to be non-negative number between 0 and 1 and sum up to 1. And that requirement is called unitarity of S matrix. And he discovered that in order to do that, he needed to introduce some unphysical degrees of freedom, which he thought was a very funny thing, but he thought he needed to do that. This is actually a very famous photograph of Richard Feynman and Paul Dirac. It was taken in Warsaw in 1962 when the conference where Richard Feynman presented this result. It's very interesting. In the proceeding, we can read about his presentation and interesting discussion afterward. This discovery of Feynman, which was introduced because of his needs to understand quantum gravity, led to a very important development. 5 years after that, DeWitt and independently Faddeev and Popov formulated this unphysical degrees of freedom as what is now called the Faddeev-Popov ghost, which played an important role in 5 years later by Gerhard Hooft and Tini Bertman, who was a faculty member at the University of Michigan, where they used this formulation to quantize successfully the Amir theory, for which they received the Nobel Prize. And then a year after, David Politzer and David Gross and Frank Wilczek used this Amir theory to discover the asymptotic freedom of QCD, which basically shows that QCD is a correct theory of strong interaction. And for that, they received Nobel Prize. So the study of quantum gravity inspired lots of very important development in high-energy physics too. But we are not done yet. We are, I don't know, depending on how you measure things, we may be yet still halfway through the progress toward unifying general relativity and quantum mechanics. So I want to tell you first why this has been so difficult. I feel like I'm like an undergraduate student coming to professor's office explaining why I couldn't do the homework yet. But here is my excuse. Okay, so the typical excuse that people give is that if you have this Einstein's general relativity, which is described in terms of this action, cosmological constant, Einstein-Hilbert action coupled to finite number matter field, this theory described this by this Lagrangian is not renormalizable. And therefore, we cannot use it to compute quantum gravity effect reliably. Now, but this is a true statement. But this is not the whole story. That's where I would like to start my lecture today. So for example, if you are a nuclear physicist like Professor Wu, you describe theory of pions and baryons, like protons and mesons, using some low-energy Lagrangian like this. And this Lagrangian is also not renormalizable. But you can still use this to calculate quantum effect reliably. So for example, as far as you are interested in studying phenomena whose energy scale is much smaller than this parameter f, which in this case is 185 mega electron volt, you can actually reliably calculate this effect. So what you do is that you are interested in calculating certain observable, be it S matrix or spectrum. Then you try to expand this observable in terms of the energy over f or momentum over f and expand in power series. And you can actually see that each term in the expansion can be calculated systematically. There are infinities that you need to renormalize, but you can do that with finite number of counterterms. So renormalizable, non-renormalizable theories are okay, as far as you are interested in calculating low-energy quantities. So this idea was put forth by Ken Wilson, who was actually a grad student at Caltech. And so this framework is called Wilsonian effective theory. So this is actually this consequence of the fact that our physical world is hierarchical. So here's a caricature of a hierarchical world. So we are about a meter here. If you go to a billion times bigger than that, it's like the orbit of moon going around the Earth. And it was the insight of Isaac Newton to discover that the law of gravity describes the falling of the atom, and the moon going around the Earth is the same law, the universal gravitation. If you go billion times more, you get to the size of galaxies, and I had a very interesting conversation with cosmologists this morning. Oh, by the way, one of the pleasure of coming to this lecture has been to meet with distinguished faculty in physics at Michigan, and I had lots of fun talking to them for the last couple of days, and thank you very much for everything. And so this morning I had a very interesting conversation as a cosmologist, understanding the development of galaxies and the new physics. And if you go to yet a billion times more, you get to the edge of the visible universe, and you see the light coming from the beginning of the universe. If you go to the shorter distance, if you go to the opposite direction, billions of meter, you get to about the size of DNA. So nanoscience, nano is 10 to the minus 9. And if you go to one more nano, then you get to the shortest distance that we can currently observe directly by experiment. The CERN's Large Hadron Collider observe phenomena at nano times nanometer. And in each of these scales, we have effective laws. And so, for example, if we want to know about the gravitational effect of the moon, you don't have to understand the quantum mechanics in nanoscale. You have appropriate effective laws, in this case, it's Newton's theory of gravity. Okay? So in each scale in physics, you have different laws. And one of the things I also want to mention is that so going toward larger direction is often called in physics emergent, while going toward the shorter distance direction is called reducing it. So we believe that if you go to shorter and shorter distance, you get to more and more fundamental laws of nature. So that's sort of effective description of nature. And this has been very useful because if you had to know about atomic physics in order to know about the motion of the moon, we would not have discovered this wonderful physics. So nature has been very kind for us in that sense. So this is a Wilsonian view that the pion theory is a low-energy approximation to more fundamental laws of nature, which in this case is quantum chromodynamics, QCD. And pion theory, which is described by this Lagrangian that I presented here, can in principle be derived by performing the quantum mechanical functional integral of QCD by freezing low-energy degrees of freedom. And this idea is called low-energy effective theory. So low-energy effective theories are typically not renormalizable, so you have divergences. But as far as you are considering low-energy expansion, then each term can be calculated with finite number of counter terms, and predictions are reliable, and you can compare with the experiment. So there is nothing to worry about low-energy effective theory. And Einstein gravity is also an effective theory in the sense that it can be used to make reliable prediction, including quantum effect, provided that energy and momenta are much less than its cutoff scale. That cutoff means that threshold above that scale requires more fundamental laws. And in this case, it's called the Planck scale that will appear later in my talk. So for example, the Hawking radiation from black holes, that was very important prediction of unification of quantum mechanics and general relativity, was done by using this kind of effective field theory calculation. Fluctuation of cosmic microwave background radiation, which has been observed by the CMB detectors, those are supposed to be caused by quantum effect during the inflation, although inflation is still a hypothetical model of the early universe. But you can actually calculate this effect, and then you can compare with experiment and observation. This is actually one of my favorite examples. This is a quantum correction to the Newton's potential. So Newton's potential has 1 over R laws, and proportional to the product of mass and Newton constant. But then there are corrections. And the first 1 over R correction is actually classical relativity effect. And for example, you can use that to incorporate motion of the mercuries and things like that. But then there are quantum effect. There is h bar in it and 1 over R squared. And the important thing I would like to stress that, for example, you can calculate this coefficient, 41 over 10 pi squared, very reliably. This is actually the correct number. And this number, in this case, in particular case, is just a calculation, one loop quantum mechanical effect by Einstein gravity. And if you have matter field, you have different number. But you can calculate these coefficients. And then this is actually the correct answer for 1 over R expansion. So you can actually calculate Einstein gravity, the quantum effect of Einstein gravity in this way too. So why do we need quantum gravity? Well, there are 2 things I would like to mention. So one is that there are very interesting theoretical questions that you want to address that you cannot understand by doing this kind of low energy expansion. So for example, how did the universe begin? What was the things like that the universe was like before the inflation? Can you derive inflation model from the first principle? What's the nature of dark energy? how are general relativity and quantum mechanics be reconciled in quantum black hole? For example, yesterday I had a very interesting conversation with Fred Adams, and he asked me the first question well, how you describe the beginning of the universe using quantum gravity. Unfortunately, I didn't have an answer to his question because we are still working on this. And this is one of the questions that we would like to understand. So maybe we ask the same question in 10 years from now, maybe. And well, maybe 5. I hope to make some progress towards that direction. And, but today, I'd like to talk about the second point, which is that the very question of this Wilsonian approach may not work with gravity. So this is, if there is one sort of message I would like to give to you today, is the point that this kind of Wilsonian low energy effective theory approach may not work with gravity. The gravity is very different from other forces of nature. So they say that history doesn't repeat itself, but it often rhymes. And they often attribute it to Mark Twain, although I think that the original citation is not known. So people started to explore shorter and shorter distance to find more and more fundamental laws of nature, the biology, molecules, atoms, and nucleus, and the standard model of particle physics. And so the question you might ask is that if you go to shorter and shorter distance, you find more and more fundamental laws of nature. So does this go forever? Or does it end somewhere? So that's the sort of first question that I would like to pose. And this is related to the point I would like to make, which is gravity is different. So let me tell you what I mean by that. So one way to probe short distance is to build a powerful accelerator. The more powerful the accelerator is, the shorter scale that we can probe. And it's because, for example, of the fact that if you have energy, the typical wavelength of the particle associated to it goes like inverse of the energy. So if the energy is bigger, then you can see shorter and shorter distance scale. But Albert Einstein said E equal mc squared. The Phil Nansen kindly mentioned some of my popular science books. So this is actually the cartoon that I drew for one of my science book. So E equal mc squared. So that means that if you have energy, you have mass, and if you have mass, you have gravity, and if the mass is very big, it forms a black hole. So eventually, if you build the accelerator so large so it reaches the Planck scale, then you'd create a black hole. And so if you have the situation where you have mass m in this range, then one of the limit for the length scale is inverse of the mass, inverse of the energy, which is the same formula that I wrote over here, except E equal mc squared. But on the other hand, if you have a black hole, there is an event horizon, inside of which is not observable in any physical means. And interestingly, that diameter of the event horizon grows now with energy. And in four-dimensional space-time, it's linear in the mass. So Compton wavelength goes inverse of the mass, and the Schwarzschild diameter grows with mass. So if you optimize it, there is actually a shortest distance you can probe with this method. Namely that if you raise energy for a while, this is much smaller than Compton wavelength, so you can build bigger and bigger accelerator and probe shorter and shorter distance. But eventually, it reaches the Planck scale, and then this Schwarzschild radius becomes competitive. So there is a lower bound for this. And we cannot probe phenomena shorter than this lower bound, which is called Planck length. Okay, so this is where the Planck length comes in. Oops, something happened. Oops, page doesn't move. Okay, so we cannot probe phenomena shorter than this Planck scale. So in physics, we often take the attitude that if there is a phenomena that cannot be observed even in this kind of Gedanken experiment, even in principle, then we interpret that it doesn't exist. So namely that, so that means that, actually the notion of distance shorter than Planck scale should disappear. So that means that for the last 400 years, we have been sort of marching towards shorter and shorter distance to find more and more fundamental laws of nature. But this march toward the more fundamental laws of nature would terminate at the Planck scale. So this is why sort of gravity is very special and is different from other forces. So I'm repeating myself. Historically, the exploration of high energy, namely short distance, has revealed more and more fundamental features of the nature. But we expect, because of this and many other arguments, that this hierarchy of scale will terminate once we complete quantum theory of gravity. And one way to think about it is that gravity turns high energy to long distance rather than short distance. High energy physics cannot be short distance physics anymore. And another way to say it is the separation of scale that separate different length scale, and you have effective theory for each scale, end. So this leads to this idea called the swampland that was formulated by Qumran Buffer in 2005, that with gravity, arbitrarily low energy theory is not guaranteed to have consistent ultraviolet completion. That in the standard Wilsonian approach, in principle, you can write down any low energy effective theory consistent with symmetry and the particle content of low energy, and you expect that to have consistent ultraviolet completion, which is that you can embed the theory in consistent mathematical framework. Qumran Buffer pointed out the possibility that that's not the case with gravity. So in fact, for the last 20 years after he suggested this proposal, we have found that there are constraints on low energy effective theory that cannot be captured by the standard Wilsonian paradigm. So the question is, can we identify and derive them from the first principle? So I would like to today present a proof of concept that indeed this low energy effective theory, the Wilsonian paradigm, breaks down with gravity. They do not have immediate observable consequences. These are proof in principle in this mathematical construction, but I hope that I will be able to show you and that those conditions exist, and so therefore can exist in a more sort of realistic situation. Okay, so that's what I would like to do today. So I'm from Japan, and in the tradition of Japanese storytelling, when the talk goes to the main subject, one is supposed to take off the jacket. So that's what I'm going to do, but then I have to take aside my microphone, which I neglected to move. So can you hear me? Okay, so now I'm in the proper attire to get to the main point of my talk. Okay, so I would like to actually derive those constraints in low energy theory in the more sort of mathematical or hypothetical framework which we can control, which is gravitational theory in negative cosmological constant. Our universe has positive vacuum energy, so it's not what we are in it. But as a mathematical construction, we can ask, well, what is the low energy effective theory or gravitational theory in this negative cosmological constant space where lambda is negative here? And it's called the anti-Dojita space. So if you consider spatial section of this, it's a hyperbolic space. The famous counterexample to the fifth postulate of Euclid, that if you have a line and if you have another point, you can have a parallel line that do not intersect, and there's only one of them. The hyperbolic ball is the first counterexample to the fifth postulate, and you add time, and then you get here anti-Dojita space. Okay, and then, so this is actually a very ideal situation where we can discuss sort of proof of concept, because there is a work by Juan Maldacena, in which he showed that any quantum gravity theory, be it, well, it was originally discovered in string theory, but we believe now that it's applied to any possible quantum theory gravity in d plus one dimensional anti-Dojita space, which is described by this kind of solid cylinder. is equivalent to scale invariant quantum field theory, particular type of quantum field theory which has particular symmetry called scale invariance, often called CFT, conformal field theory, in one less dimension. So this is called ADS, CFT correspondence. So theory with gravity in D plus 1 dimension is equivalent to theory without gravity in D dimension, one less dimension. Okay, I'll tell you later how this kind of idea works in a little bit more microscopic detail. But let me just first present this as sort of a first principle of quantum gravity in this setup, that anything about quantum gravity in this negative cosmological constant space can be described in conformal field theory. So you can try to prove a statement about gravity in this context by using technique of conformal field theory, which is more well-defined and mathematically rigorously carried out. So this ADS-CFT correspondence is an example of holographic principle where we think that all the gravitational phenomena inside of this solid cylinder can be described by projecting data to two-dimensional surface. And in string theory, it is implied by consistency of the description of black hole. But as I said, we believe that this holds for any consistent quantum theory of gravity. Okay, so what I'm going to do today is to use this framework as a first principle and use conformal field theory as a definition of quantum gravity in uncertain space. And if you accept this premise, then we can identify and, in fact, mathematically prove various low energy constraints on gravity. So that's what I would like to do. So, as I promised, I will prove several non-Wilsonian statements about quantum gravity in the remainder of half an hour. So there have been several statements we can talk about. The quantum gravity has no arbitrary parameters. That's one of the first statements that was stated. And we can quantify this to what's called distance conjecture. Don't worry about the equations. I will explain that later. And then there is also expectation that quantum theory or consistent quantum theory of gravity has no symmetry. Okay, so this is very peculiar. That the symmetry has been very important principle in understanding physics. But it has been speculated 1957 that consistent quantum theory of gravity should not have symmetry. So I will explain why it is. And then there is a quantified version of that, which is called weak gravity conjecture. And I will discuss that later. But first, no arbitrary parameter. And its relation to the distance conjecture. So in fact, the absence of parameter is probably the earliest Swampland condition, which was stated in the autobiographical note of Albert Einstein, which was first published in 1949, which is why I mentioned this time. And this is actually very interesting reading. And there is actually a chapter in which he actually introduced the notion of natural units in a very nice way, that there are some fundamental constants of nature, Planck constant, Newton constant, and speed of light. And if you combine those, you can measure any physical object, observables, in terms of dimensionless constant. So he explains that then the only dimensionless constant occur in basic equation of physics, that you can have a variety of different potential equations that can describe physics, and it can have parameters. And but he didn't like that parameter. So he goes on to say that concerning such, I would like to state a theorem which at present cannot be based upon anything more than upon a faith in the simplicity, namely the intelligibility of nature, that there are no arbitrary constants of this kind, that all the constants should be derivable in principle. So that's he expressed such expectation in his autobiographical note. Now we can prove this actually in the context of ADS-CFT, so that's what I would like to do. So Qumran Baffa and I, a year after Baffa formulated Swampland conjecture, formulated Einstein's statement a little bit in modern language, which says that every parameter in quantum gravity is an expectation value of some dynamical field. For each parameter, seemingly parameters, there must be some dynamical field in the gravitational theory, and that should be one should be able to vary it by changing its expectation value. Constant of nature is not really constant. Every constant we should be able to vary because it's the expectation value of dynamical field. So that's what Qumran Buffer and I claimed based on many examples we know in string theory. Okay, so actually we can prove this if you assume ADS-CFT. So let me outline how the proof goes. Okay, so supposing that there is a gravitational theory with continuous parameter lambda. So that means that there is a Lagrangian for gravitational theory, which contains Einstein's equation, Einstein's Hilbert terms, cosmological constant, etc. But it also has parameter in it. The Lagrangian depends on some parameter. Okay, so that's reasonable to understand. But then there must be a corresponding parameter in conformal field theory. The conformal field theory may have Lagrangian to describe this one, and that Lagrangian should contain this same kind of parameter, corresponding parameter. Now, if you have a parameter in conformal field theory, you can deform it, and deformation of that is generated by particular types of term in the conformal field theory Lagrangian called exactly marginal terms. Okay, so but there is actually a dictionary between conformal field theory and gravity in Einstein space, and if you follow the dictionary, then you find that for every operator there is a corresponding dynamical field in the gravitational theory. In particular, if you have exactly marginal operator, there is a corresponding massless scalar field such that their parameter is equal to the expectation value of this dynamical field. That's exactly what Einstein claimed in the autobiographical note, and that's how we formulated this, the first of the distance conjecture. And namely, the parameter is an expectation value of scalar field. So whenever you have parameter, so this line of thought proves that whenever you have parameter in the gravitational theory in Einstein space, there is a dynamical parameter, and the parameter is an expectation value of scalar field. Okay, so this is sort of very short proof of this rather interesting statement. It is interesting, but it's actually not useful. So this is like very, so when I'm not going to do it today, but in some of the physics curriculum on that subject, I often draw two-dimensional diagram. The vertical axis is useful to useless, and the horizontal axis is rigorous to speculative. And like many things in life, things tend to lie on the diagonal axis. And so I try to sort of move this towards a more useful and rigorous corner. But this is an example where you can, of the statement which you can prove rigorously, but it's not by itself useful. Because what appears to be a parameter in low energy theory may be fixed by potential in a more fundamental high energy theory. So for example, we know that standard model of particle physics that has been verified to this in the Large Hadron Collider. Yesterday, actually, I had a very interesting conversation with a high energy experimenter doing a very interesting check of standard model of particle physics at CERN. And this model has 19 parameters, or we know that there are also neutrino has masses, so if we include that, there are 7 more, so 26 parameters. The lambda CDM model, which is a standard model of evolution of the universe, the lambda CDM model has 6 parameters. But we don't believe that those theories are in swampland, that even though there are no corresponding dynamical field in low energy. And the reason we believe is that they may be determined by dynamical field, but those dynamical field has a potential whose value can be fixed. So we don't see that in low energy. So this is not very useful then, that even if you have a parameter, you don't know whether there is a dynamical field and how these values are determined. So we went on, Qumran and I went on to explore more examples in string theory and formulated more statements which seems to be true in all known string theory. So for example, if you have a parameter, space of parameter in quantum gravity, there is always a direction which can go to infinite distance. So for example, if you consider string theory in 10 dimensions or M theory in 11 dimensions, and if you compactify this theory like Karuta-Klein, that Oscar Klein was here at the University of Michigan, and I understand he actually did this work about the emergence of non-abelian gauge theory from compactification while he was actually a faculty member at the University of Michigan. So in this kind of constructions, for example, the size and volume of this internal space can be parameters. And if the size grows, the distance to the infinite volume is actually infinite in appropriate length scale. And if you do that, the Karuza-Klein excitation becomes very light. So the second conjecture we formulated is that whenever you go to that kind of infinite distance, then there is always a tower of light particle emerging. And we can formulate this in a more sort of careful way. And so in order to, I don't want to bore you with all these equations and sentences, except to say that we actually quantified how this light degrees of freedom emerges. And if we can actually quantify, so what I mean is that if you go to the distance in the moduli space, the space of parameter of gravitational theory, in the infinite distance limit, then there appears light degrees of freedom, light particle whose mass goes like exponential in the distance. It goes like decays exponentially. So if we can actually, so at that time we thought that if we can actually bound this parameter, then we'll have a very useful constraint in low energy theory. So I'm very happy that this year actually we were able to do that in a very simplified setup with Ihan Wang, who is assistant professor at NYU, and me. And we actually were able to prove that in the class of gravitational theory, that actually if you go infinite distance, mass indeed decays exponentially, and this parameter, coefficient alpha, is bound below by Planck scale and bound above by the curvature scale of Antidata space. So in particular, what this shows is that if the scalar field rolls beyond the Planck scale, the low energy effective theory should always break down. Okay? So this is actually very significant if something like that is also true in the inflation model, in a more cosmological situation, because typically, in order to have exponentially large expansion, what people call 60-folding of the inflationary universe, then it requires that what is called inflaton analog of this phi to change its value more than the Planck scale. But this type of theorem that we have proven shows that if there is a scalar field whose expectation value changes more than Planck scale, actually quantitatively here it's two-thirds of Planck scale, then low energy effective theory should inevitably break down by having some lot of light degrees of coming in, light degrees of freedom coming in low energy. So this, if something like that is true in our real world scenario, then it can put strong constraint on inflation model. So I think research in this direction is very interesting. And so there was a speculative paper that my colleague Scarassi and Irene Valenzuela wrote some years ago, where they took our conjecture on face value and assume that it applied to the real world cosmology and see what you get. And then they found actually that it put actually rather stringent constraint on the polarization of cosmic microwave background radiation because it puts constraint on how much inflaton travels. And so the amount of travel of inflaton is related to the amount of polarization of cosmic microwave background radiation. So there was actually an interesting story. I think it's about 2014 when BICEP2 experiment announced that they have found primordial polarization of cosmic microwave background radiation. At that time, actually, I was a deputy dean of physical science at Caltech. And so we got to know the result like a month before. So I remember I was working in the dean's office. And then because Caltech was one of the main players of this BICEP experiment. So Dean came in and said, you know that the BICEP has a result. And I asked, well, what's the value of R? He said 0.2. And they said, well, this is great. It's going to kill string theory. And the reason, there's a reason for this, for my pronouncement, because you can see that my distance conjecture would give you upper, so vertical axis here is the amount of this inflaton field should travel. And the horizontal axis is the amount of what's called tensor polarization of CMB. And there is a lower bound for this amount of travel of inflaton, because in order to have large R ratio, that's a tensor scalar ratio, inflaton has to travel very much. But our distance conjecture says that this inflaton cannot travel very much. So there is a tension that there is an upper bound in blue and lower bound in orange, and they meet at 0.2. So if R were greater than 0.2, then it would not have been possible to realize it in string theory. So that's why actually I said, well, it's great. It's going to kill string theory. I should have written a paper about this, but I didn't. So, but he remembers it. Tom Solfer, who was the chair at the time, actually teased me about this afterwards. So this was just to demonstrate that extending this kind of result to the more realistic situation is potentially have very interesting consequences. So this is the sort of line of direction which started with Einstein, that there are no arbitrary parameters in gravitational theory, and led to our distance conjecture. There is another line which says there is no global symmetry, and that was actually John Wheeler. So I consider this as the second earliest swampland condition, so this is actually Annals of Physics article that he and Minsner wrote, and in which he basically said that there are no global symmetry in quantum gravity. And so the idea is sort of motivated in many ways. For example, you can have black hole in quantum gravity, and you can, suppose you have like two species of particles with identical properties, and you can throw one of them, but if the particle is inside of a horizon of black hole, then you don't know which one is thrown in. And then if the black hole decays, emits radiation and decays by Hawking radiation, then that information is lost forever. So therefore, the notion that there is a global symmetry to distinguish these two types of particles will be lost by quantum gravity effect. So that's sort of the idea. And but this actually again can be proven, and in fact Daniel Harrow and I proved this 6 years ago or so using ADS CFT correspondence again. And this actually idea makes use of Noether theorem, generalization of Noether theorem. So Noether theorem is a very important theorem in physics. About half of the audience are physicists, so I believe you know Noether theorem, that whenever you have a global symmetry, there is a conserved charge. And that's a Noether theorem. And this is true, this is easily true for continuous symmetry, and this is the original Noether theorem. So whenever you have some symmetry in the physical system, there is a conserved current acting on the Hilbert space, and then you can actually construct the generators on the Hilbert space which generates the symmetry by exponentiating the integral of the current. The important thing is that it's an integral of the current on the Cauchy surface, the initial value surface. So if the surface is divided into disjoint union, then this unitary operator becomes product of operator acting on each region. So if you have a spatial slice of the space, and if you have a Noether charge acting on it, then if you divide the space into half, it becomes product of the operator. So that's sort of a main feature of Noether theorem. And it was actually proven by rigorous algebraic quantum field theory people that this is true even for discrete symmetry. So this is actually, this is called generalized Noether theorem. And, but this is actually in tension. This is in contradiction with how holography works in quantum gravity. So this was discovered by Almheri, Dong, and Harrow some years ago, that people are interested in how holography in ADS-CFT works in a sort of microscopic way. So they came up with a very interesting insight. So as I said, in ADS-CFT correspondence, you have gravitational theory in d plus 1 dimension in isolated space. But it's supposed to be equivalent to conformal field theory in d dimension. So conformal field theory has one less dimension. So where do you get extra 1 dimension coming out of gravity? And what those people discovered is that this additional information is coming from quantum entanglement on the bound in this conformal field theory. And in particular, the way that this reconstruction of local information appears is closely related to the idea of quantum error correcting code. That is that, so in classical computer, like I have in laptop, for example, they use error corrections. So we have this machine is under various thermal disturbances, so you need to continuously correct information. And the way that a classical computer does is to introduce redundancy. You make same copies of the same set of information and check various things like parity checks to make sure that information is held intact. In quantum computer, you cannot do that because there is a thing called the quantum no cloning theorem or the no Xerox theorem that says that there is no unitary process which maps one state into tensor product of the same copy. So people came up with a very clever idea called the quantum error corrections, in which they actually is also encoding information in redundancy, but in a way that quantum entanglement between different copies carries the information. And so this idea, it was shown that this is exactly how it works in quantum gravity. And however, if you assume that, then this actually shows that you cannot have quantum gravity having global symmetry. And it follows from the following point that if suppose you have some local object which carries a charge with respect to some global symmetry, then you can actually find a contradiction. Because if you have a boundary divided into various segments, then the unitary operator to implement the symmetry is product of local operator. But if you have this kind of product action, it cannot change the entanglement nature. So it cannot even, in principle, act on this operator. So this kind of argument led to the contradiction, and it showed that there is no global symmetry in quantum gravity. In fact, this leads to some interesting development that I mentioned that there are two lines of Swampland condition. That one is that there are no arbitrary parameter in quantum gravity. And the second is no global symmetry in quantum gravity. And there are two different lines of insight into low energy effective action. But it turns out that these are actually the same statement. That for the last decade or so, the notion of symmetry has been in quantum field theory and quantum mechanics has been greatly generalized thanks to the work by Davide Gaiotto and my colleague at Caltech, Anton Kapustin, Nati Zyberg, and Willett. And so one of the generalization is the following consequence that absence of parameters that Albert Einstein mentioned in his autobiography note can be regarded as some absence of particular type of global symmetry. And in that way, you can actually unify these two ideas. But again, just like absence of parameter by itself was not a very useful constraint on low energy theory, absence of global symmetry itself is not a useful constraint. For example, the standard model of particle physics preserves B minus L, baryon number minus lepton number symmetry, which is supposed to be a global symmetry in standard model of particle physics. So it can be violated in high energy. But unless we know how this breaking happens, in what size, and in fact, yesterday, Fred and I had a very interesting conversation about the rate of proton decay and its consequence to the far future fate of the universe. And so those questions, we want to know how strongly this type of global symmetry is broken. And we don't know from this absence of global symmetry theorem. And this is analogous to the absence of parameter in Einstein's theory, that what seems like a dynamical parameter may be expectation value of dynamical field fixed by potential. And similarly, what seems to be a global symmetry may be some accidental symmetry in low energy. So in order to make more useful prediction, Nima Alkani-Hamed and his collaborator formulated what is called weak gravity conjecture. So this is an idea that any low energy theory described by Einstein gravity and Maxwell field and finite number of matter field, if it has a consistent ultraviolet completion, then there must be a particle with charge q and mass m satisfying this inequality. So this is a weak gravity conjecture. And so again, Daniel Haro and I came up with some argument using ADS correspondence which support this more refined version of conjecture. So this actually has a rather interesting consequence in our real world. So in previous presentation in earlier, I mentioned that even though this distance conjecture is proven in ADS CFT context, but if you assume something like that is true in our real universe, then it would have a very important consequence in the prediction of inflation. And Kumran Baffa and I did something very similar to that if you assume this weak gravity conjecture also in our real universe, then it actually have a very interesting inequality between dark energy and neutrino mass. So you might be aware, you might know that actually the amount of dark energy in our universe is very close to the non-upper bound of the mass of neutrinos. So the dark energy density has a dimension of mass to the fourth. So if you raise the neutrino, we don't know the absolute value of the neutrino mass. We know the difference of the neutrino mass. But if you assume that the difference of neutrino mass is of the order of neutrino mass itself, and then consider force power of that, that actually is roughly the same as the amount of dark energy of the universe. Why is that? Well, so it's not known, but it's an interesting coincidence. And Kumran Baffa and I pointed out that, in fact, if you assume weak gravity conjecture, then from that you can actually deduce the kind of inequality. Actually, one of the cosmologists I met today working on DAISY experiment told me that he now have a more stringent constraint on the upper bound of neutrino mass. So maybe I should check with the DAISY result to see whether this conjecture still holds. But when I last checked it, it was sort of on the verge of almost being included and excluded, depending on whether neutrinos are Majorana or Dirac. So this is actually also potentially interesting direction. So I think it's interesting that there are actually non-trivial. So all these constraints are not obvious from Wilsonian point of view. And but you can actually derive this, some of them from first principle. And if something like that is true also in our real cosmology, real universe, then it has actually important consequence in our observation and experiment. Well, scalar field has potential. Inflation model has scalar field with potential. So it would be good to have constraint on scalar field also. So this is something that also Kumran Baffa and I worked on, and we tried to put some constraint on the model of cosmology. But recently it was actually found, it's not my work, but it's so interesting, so I thought I should mention it, that you can also derive constraint for the potential for scalar field from first principle in the context of ADS-CFT correspondence. So this is the following kind of situation. So supposing you have low energy theory where you have Einstein gravity, Einstein-Hilbert term, and kinetic term for a bunch of scalar field and the potential. And the value of potential determines the amount of dark energy in this uncertain space. So there is this inequality in general relativity called the Penrose inequality. So this is the following idea that if you have a large amount of mass in some part of the space-time, then the light starts bending. And if all the light cone bend toward inside, it creates what is called apparent horizon. That in order to see whether apparent horizon is the event horizon or not, requires that you need to see the infinite future. But apparent horizon is determined by the condition locally, by just observing how the light cone bends. And there is the inequality that Penrose proposed is the inequality between the mass, total mass in the region, and the size of the apparent horizon surrounding it. In asymptotically flat space-time with zero cosmological constant, it's a conjecture. It's motivated by cosmic censorship hypothesis. However, in uncertain space, you can actually prove this using consistency of conformal field theory. And this was done by Gary Horowitz and Netta Engelhardt about 5 years ago. And the inequality takes the following form, where M is the mass of the region and A is the size of the apparent horizon. So there is this kind of inequality. This is an inequality for four-dimensional isolated space, but you can derive it in other dimensions. There is an interesting inequality between Newton constant and mass and the size of apparent horizon. Okay, so what it has to do with the potential. So Asmund Folkestad, who was a graduate student of Netta Engelhardt, actually showed that if you consider this type of scalar potential, and if you assume certain kind of type of potential, you can actually create an initial condition that violates the Penrose inequality that I wrote down over here. And it's actually a large region. So if you parameterize, for example, potential for the cubic term and the fourth quartic term with coefficients G3 and G4, so then there is a vertical axis is G4 and horizontal axis is G3. And this half of this region is excluded by requiring that the Penrose inequality violating initial condition cannot be constructed. So if your potential is in this region, then your low energy theory is in swampland. So it cannot be derived from consistent quantum theory of gravity. So you can actually derive this kind of interesting constraint too. So I'm supposed to end at 4 o'clock, so it's 4 o'clock, so I should end. So there is a one sentence summary of my talk, which is gravity is different. And so that's what I would like to tell you about today. But expanding it a little bit more, there are constraints on low energy effective theory of gravitational theory that cannot be captured by the standard Wilsonian paradigm. And I hope that I have been able to demonstrate to you mathematically that this is a true statement, that there are constraints. It's not a realistic situation, but proof in principle that you can prove that gravitational theory in this setup has no arbitrary parameters and no global symmetries. And in certain cases, you can actually quantify this in the form of distance conjecture. And with gravity conjectures that in the gravitational theory in uninterrupted space, you can quantify and prove parts of this conjecture as from the first principle. So of course, I would like to extend this result and generalize them to space-time with asymptotically flat or even accelerating universe. And so that's sort of what I'm working on right now, but this has been the report on the progress. Thank you very much for your attention.
Okay, thank you so much for that talk. And we do have time for some questions. And if you do have a question, please raise your hand, and then either I or one of the 2 microphone runners on the sides of the hall will give you a microphone so we can all hear. Question over here.
The microphone is not on.
No? Okay. So just to see that I understand your proof. So you showed in ADS, if you have an arbitrary parameter in your Lagrangian, you can rewrite it as a CFT on the boundary, and there this parameter is the expectation value of some field.
Right.
So I guess the same holds for the cosmological constant. This is a parameter in my Lagrangian, and it would be an expectation value of some dynamical field.
Well, if
on
there
the
is a
CFT.
holographic dual, yes.
Okay.
So in our expanding universe, there can be a parameter, and in fact, the lambda CDM model has 6 parameters. But we don't know whether there is a corresponding dynamical field, because there is no alternative formulation yet which we can use to derive that statement.
But you still have this constant, you just know it's 0, it's negative, but you could write it as a CFT with a new field, and the expectation value would be negative or not. Do I understand correctly?
No, I'm not sure I understand your question yet. So, for example, this setup of ADS-CFT correspondence applies only for space-time with asymptotically negative cosmological constant. So, it doesn't apply to the expanding universe.
Well, then the rest of my question, okay. So then just very generally, since this only holds for a negative curvature, like what is even the approach to generalize this? Are there like physically intuitive reasons why it should generalize or not?
There are two possible things one can think of. One is that to consider family of theories for which ADS scale or the inverse of cosmological constant goes to zero. There is a family. There is indeed a family of gravitational theory in isolated space with family of corresponding conformal field theory, where the ADS radius goes to can become arbitrarily light. So therefore, you can actually approximate this statement, the approximate statement in flat space, asymptotic flat space, arbitrarily well by considering this family of gravitational theory in isolated space. Now, positive cosmological constant, I do not know. But in fact, Qumran Baffa and I have conjectured that those theories do not exist. That what seems like a positive cosmological constant or positive dark energy should be all expectation value of some field. So that's sort of more a difficult situation. And another direction that is more ambitious, and so this is potentially implementable with the current technology. That is to consider this family of theories. And another possibility, which is more ambitious and I hope is achievable, is to formulate this type of holographic principle to asymptotically flat space or even Logita space. And there have been some proposals about that. Andy Strominger and collaborators has been pursuing what is called the celestial holography, which is that instead of a conformal field theory at asymptotic infinity, in the spatial infinity, like in isolated space. In flat space, there are future light cone and past light cone, future infinity and past infinity. And then there can be conformal field theory located at these future light-like infinities. And so those are called the celestial holography, because these future light-like infinities makes celestial sphere. On which the Poincare symmetry acts like conformal symmetry at infinity. So there have been some proposals like that, and if these can be formulated rigorously, then that can be a basis to actually extend this more in a more robust fashion to these space-time. So that's sort of one of the directions that I'm interested in. So microphone is coming, Gordy.
Okay. We know that the Higgs boson now is, and massless particles interacting with the Higgs boson get mass. And so it's a particle that, for that to work, the Higgs mass must not vanish. It has to have a non-vanishing vacuum expectation value, and that gives it a mass too. So how do you imagine that'll fit in to this picture with a little more work?
So Higgs, of course, has a potential, right? So mass of standard model of particle physics is a parameter, but it's parameterized by the potential of the Higgs scalar field.
So having a non-vanishing potential
The potential is important to, of course, determine the value of the mass and its coupling to standard model particle, right?
So that fits in with, you won't have any problem with the theorems about mass vanishing and so forth. It'll work out okay with the Higgs.
Yeah, so that's one of the reasons why I was interested in sort of understanding the situation where scalar field has, I went in the wrong direction. But towards the end of my talk, I talked about the situation where, this is what I was interested in, the case when the scalar field has a potential. And that's sort of one of the situations where this kind of approach is relevant.
Okay.
Oh, Fred is raising hand.
So I noticed when you wrote all your constraints, you put it in arbitrary numbers of dimensions. I think that's what your lowercase d was. I think it might be fun for the audience if you would to comment on what are the current constraints on the number of dimensions of the fundamental theory. You know, it started out being 26 in heteronic strings, then 10, and then 11. So how would you answer that for the general audience?
Well, like I said, the string theory construction will give you sort of proof of concept of unification of general relativity and quantum mechanics, that there is this set of theories for which the unification is achieved. And we don't know of any other credible approach for now, which has the following three important features, that it's consistent with the principle of quantum mechanics. It contains low energy gravitational theory and flat space as a solution. So there are no other approach to quantum gravity that has all these three features except for string theory. And in string theory, the d equal 11 is the highest number as we know of. And there are reasons for this. And so it's related to the fact that supersymmetry is an important feature of string theory. And if you want supersymmetry, then you cannot have arbitrarily high dimensions. And the reason for that is that, well, one of the simplest reasons for that is that if you have supersymmetries and if you assume that fields in low energy theories are in terms of scalar, spinor, vectors, and gravity, then you cannot have a higher spin field because that will not be consistent with other principles. Then the component of spinor grows exponentially. You know that the component of Dirac spinor goes to 2 to the d over 2. So it's the dimensions for fermions grows exponentially in dimensions. The number of components of fermion grows exponentially in dimensions, whereas the number of components of bosons grows at least polynomially because the vector component grows like linear. The graviton grows quadratically. So from that, you can already see that there must be in order for the space-time supersymmetry to exist, there must be upper bound on the dimensions. And so that I think is one of the reasons so far why we have seen the upper bound on the dimension of the consistent theories. And I do not know whether that's an absolute upper bound, but it's a significant upper bound that is well motivated.
Yeah, allow me to put on this side all the experiments physicists and non-physicists have made over many, many years. And here, the standard theory we use every day. Other than the fact that having so many parameters is very unsatisfying.
So many parameters, you mean in the standard model you have 20?
Standard model and all that.
Yeah, 28,
Is there
26.
today an experimental thing we cannot explain with a standard theory?
Sure. There are things, like, for example, nature of dark matter. So we do know that there are dark matters in the universe. We don't know what they are. We know it exists. They are not in the 19 particle in the standard model of particle physics. So that's one example. We know that the dark energy universe has dark energy, and it can be easily explained by cosmological constant, but it doesn't explain why it's so small. And it may well be dynamical, then it's how the scale is determined. For example, this is one of the possibilities that I'm presenting where there must be a positive cosmological constant if you assume neutrino has masses. And so there are some directions like that. So there are actually, indeed, I agree with you that the standard model of particle physics with this parameter can explain everything that is happening in Large Hadron Collider. And I heard a very impressive thing about that yesterday from one of your experimental colleagues. But for example, we don't know, even within a relatively sort of down-to-earth object, like, for example, neutrino is known to have mass. But strictly speaking, it's not part of the standard model. For example, we don't know whether neutrino is Majorana or Dirac. And depending on that, you have different number of parameters and different mechanisms to give rise to mass. So I think there are unknown. And we do know that there are unknowns beyond the standard model of particle physics that we would like to explain.
I have a follow-up to that question.
Yes?
So if the graviton were to be discovered, for example, and gravity were to be quantized, to some level, how would the swampland regime change as a result, or how would these constraints change, or can it account for this kind of new particle?
Sorry, so let me, can I repeat the question? So you asked, supposing graviton exists, which seems to be a reasonable prediction of quantum gravity in the low energy, then what's the...
Then how would it impact these constraints that we were talking about, or the swampland regime? Like, how would those change, or does it already take into account a possible quantized graviton?
Well, so actually the graviton is an interesting question, but the swampland conditions that we have discussed so far themselves do not exclude the existence of graviton, or it has no implication of whether graviton exists or not. And in fact, if you assume low energy effective theory, which can be consistent with all known swampland conditions, you can quantize it in a way that I mentioned earlier, that in energy scale much below the Planck scale, you can quantize and find consequence consistently. And then it's totally consistent with everything we know that the quanta of graviton should exist. Now, there is a very interesting question, however, of how do you go about detecting gravitons? Because it's very weakly interacting. And so there have been actually some paper, including the one by Freeman Dyson, about how to go about building experiment. And there are some people say that if you build detector, since graviton interact so weakly, that if you try to build the detectors that detect black hole, then the detector would collapse into black hole or something. Detect graviton, then the detector would collapse into black hole. But actually, there are some controversy about this. So I do not know the status of this. But apart from this type of questions, that I don't think there is. So that's a question of whether you can detect or not. But I think the existence of quanta of gravitation I don't think is controversial. Yeah, you are raising hand, I remember. Please hold the microphone.
You have my voice? Okay. So in general, relativity singularities are extremely localized. I was wondering if a quantum gravity theory can in any way smoothen these singularities, or if it is, how?
Yeah, so in certain situations, we know example where quantum gravity effect or string theory effect resolve some of the singularities. And there are a very simple kind of singularity. For example, there can be singularity where the curvature diverges in some point. And then there is a situation where if you embed this construction in string theory, then you can have a space-time where the curvature is infinite at some point, but still you can actually formulate string theory consistently. So you can actually resolve some of these singularity. Now, it's not true that singularity is always localized. For example, we expect that at the beginning of the universe, there is an initial singularity in the universe. And it's supposed to be, universe is spatially homogeneous and isotropic. So the singularity is supposed to be extended in everywhere. Of course, it's codimension 1 because it's the beginning of the universe, but so it's not localized. So there are examples of singularity which are not localized.
Any more questions? Okay, then let's thank Professor Ooguri again.